Have you ever wondered how nature uses fractional powers to create such intricate patterns? From the spiral of a nautilus shell to the branching of a fern, mathematics governs the beauty we see around us. Today, we'll unlock the secrets of fractional exponents and see how they connect roots and powers in a surprisingly simple way. By the end of this journey, you'll understand how a single mathematical concept bridges the gap between taking roots and raising to powers. Get ready to discover the elegant mathematics that nature has been using all along, hidden in plain sight within fractional exponents. Now we reach the heart of fractional exponents. There's a beautiful equivalence that connects powers and roots in a way that might surprise you. Here's the fundamental relationship. X to the power of m over n equals the nth root of x to the m, which also equals the nth root of x, all raised to the power m. Let's break this down. The fractional exponent m over n has two parts. M in the numerator tells us the power, and n in the denominator tells us the root. This equivalence gives us two different ways to compute the same result. We can either raise x to the power m first and then take the nth root, or we can take the nth root of x first and then raise that result to the power m. The remarkable thing is that both paths always give exactly the same answer. This isn't just a mathematical coincidence, it's a fundamental property that makes fractional exponents so powerful. Let's demonstrate this with a concrete example. 8 to the power of 2/3. We'll calculate this using both methods to show they give the same result. Using method 1, we first raise 8 to the power of 2, giving us 64. Then we take the cube root of 64, which equals 4. Using method 2, we first take the cube root of 8, which is 2. Then we raise 2 to the power of 2, giving us 4. Notice we get exactly the same answer. Both methods give us the same result, 4. This demonstrates the fundamental equivalence of fractional exponents. You can choose whichever method seems easier for the specific numbers you're working with. The key insight here is that the order of operations doesn't matter. Whether you apply the power first or the root first, you'll always get the same result. This flexibility is what makes fractional exponents such a powerful tool in mathematics. Now let's work through our second example, 8 to the power of 1/3. This fractional exponent follows the same pattern we just learned. Remember, when we see a fractional exponent with 1 in the numerator and 3 in the denominator, this tells us we need to find the cube root. So 8 to the 1/3 power is equivalent to the cube root of 8. To find the cube root of 8, we need to ask ourselves, what number, when multiplied by itself 3 times, gives us 8? Let's think through some perfect cubes. We know that 1 cubed equals 1, which is too small, and 3 cubed equals 27, which is too large. But 2 cubed equals 2 times 2 times 2, which equals 8. Perfect. Since 2 cubed equals 8, we know that the cube root of 8 equals 2. Therefore, 8 to the power of 1/3 equals 2. Remember this key pattern. When you see a 3 in the denominator of a fractional exponent, it always means you're looking for the cube root. This connection between fractional exponents and roots is fundamental to understanding these expressions. Now we'll work through a more complex example, 27 to the 2/3 power. This problem will demonstrate both methods for simplifying fractional exponents and help you understand when each approach might be more convenient. We have two equivalent methods to simplify this expression. Let me show you both approaches side by side so you can see how they compare. Method 1 follows the pattern. Take the root first, then apply the power. So 27 to the 2/3 becomes the cube root of 27, all raised to the second power. The cube root of 27 is 3 because 3 cubed equals 27. 3 times 3 times 3 gives us 27. Now we square our result. 3 squared equals 9. Method 2 takes the opposite approach. Apply the power first, then take the root. So we have the cube root of 27 squared. First, we calculate 27 squared. 27 times 27 equals 729. Now we need the cube root of 729. Since 9 cubed equals 729, the cube root of 729 is 9. Notice that both methods give us exactly the same answer, 9. This demonstrates the fundamental equivalence of these two approaches to fractional exponents. So which method should you choose? Method 1 is typically easier when the root calculation is straightforward, like the cube root of 27. Method 2 might be preferable when dealing with larger numbers where the root is more complex to calculate directly. The key insight is that both methods are mathematically equivalent. Choose the one that makes the arithmetic easier for the specific numbers you're working with. Now that we understand how fractional exponents work, we need to learn how to solve equations that contain them. This is a crucial skill that appears frequently in algebra and higher mathematics. The key strategy for solving equations with fractional exponents is isolation. We must first isolate the term containing the fractional exponent on one side of the equation before we can eliminate the exponent. Here's the technique. If we have x to the power of m over n equals some constant k, we can solve for x by raising both sides to the reciprocal power, which is n over m. This eliminates the fractional exponent and gives us x equals k to the power of n over m. Let's work through a specific example. We want to solve x to the 1/2 power equals 5. Notice that the variable x has a fractional exponent of 1/2. Step 2. We identify the reciprocal of the fractional exponent. The reciprocal of 1/2 is 2 over 1, which equals 2. This means we need to raise both sides to the power of 2. Step 3. We raise both sides of the equation to the power of 2. On the left side, we have x to the 1/2, all raised to the power of 2. On the right side, we have 5 raised to the power of 2. Step 4. We simplify using the power rule. When we raise a power to a power, we multiply the exponents. So x to the 1/2 raised to the power of 2 becomes x to the 1/2 times 2, and 5 squared equals 25. Step 5. We simplify the exponent. 1/2 times 2 equals 1, so we have x to the first power equals 25. Since x to the first power is just x, our final answer is x equals 25. Let's highlight our solution. We found that x equals 25. We can verify this is correct by substituting back into the original equation. 25 to the 1/2 power equals the square root of 25, which is indeed 5. Here's the key takeaway for solving equations with fractional exponents. First, isolate the term with the fractional exponent. Second, raise both sides to the reciprocal power. Third, simplify using exponent rules. This systematic approach will work for any equation with fractional exponents. Fractional exponents aren't just abstract mathematical concepts. They solve real problems we encounter every day. When architects design buildings, engineers calculate materials, or you're planning a home renovation, fractional exponents help us work backwards from area and volume to find the dimensions we need. Let's start with a common scenario. Imagine you're buying square floor tiles for your kitchen. The store tells you each tile has an area of 36 square inches, but you need to know the side length to see if they'll fit your space. We know that the area of a square equals side length squared, so if the area is 36, we need to find what number squared gives us 36. This is where fractional exponents come to the rescue. The mathematical relationship is side length equals 36 to the power of 1/2. Let's write this equation and solve it step by step. Perfect. Each tile is 6 inches on each side. The fractional exponent 1/2 gave us the square root, which is exactly what we needed to find the side length from the area. Now let's tackle a three-dimensional problem. Suppose you're ordering a storage cube for your garage. The manufacturer specifies that it has a volume of 64 cubic feet, but you need to know if it will fit through your doorway. For a cube, volume equals side length cubed. To find the side length from the volume, we need the cube root, which we can express as a fractional exponent with denominator 3. The equation becomes side length equals 64 to the power of 1/3. This fractional exponent represents the cube root operation. Excellent. The storage cube is 4 feet on each side. The fractional exponent 1/3 gave us the cube root, allowing us to work backwards from volume to find the dimensions. These applications show up everywhere in the real world. Architects use fractional exponents to determine room dimensions from floor areas. Engineers calculate pipe diameters from flow volumes. Even gardeners use them to find the radius of circular flower beds from their areas. The key insight is that fractional exponents let us reverse common geometric formulas. When we know the result but need to find the input, fractional exponents provide the mathematical tool to work backwards efficiently and accurately. Fractional exponents aren't just abstract mathematical concepts, they're powerful tools used in cutting edge scientific research, particularly in epidemic modeling, where they help us understand and predict disease spread. Traditional epidemic models divide populations into groups: susceptible individuals who can catch the disease, and infected individuals who can spread it. But real disease spread is more complex than simple interactions between these groups. The traditional epidemic model uses this simple equation where the rate of new infections depends on the product of susceptible and infected populations. But this assumes perfect mixing and immediate transmission, which isn't realistic. Fractional epidemic models use fractional exponents and derivatives to capture the memory effects and complex interactions that traditional models miss. The parameter alpha represents how much the system remembers its past states, while gamma captures nonlinear interaction patterns. For COVID-19 modeling, researchers found that fractional models with alpha around 0.95 provided much more accurate predictions than traditional models. The fractional exponent captures how the virus spreads through social networks with memory effects and varying contact patterns. When we compare predictions, fractional models show more realistic behavior. Traditional models often predict unrealistic exponential growth, while fractional models capture the gradual changes, memory effects, and complex social dynamics that actually occur during epidemics. The power of fractional exponents in epidemic modeling lies in their ability to capture the complex, nonlinear nature of real-world disease spread. They account for memory effects, variable contact patterns, and the gradual changes that make epidemics so challenging to predict with traditional mathematical tools. Even experienced students can fall into traps when working with fractional exponents. Understanding these common mistakes will help you avoid costly errors and build confidence in your calculations. The first major mistake is misunderstanding the order of operations. When students see 8 to the 2/3 power, they sometimes incorrectly think this means 8 squared divided by 3. The correct interpretation is that the entire fraction 2/3 is the exponent. This means we take the cube root of 8 first, which gives us 2, then square that result to get 4. Another common mistake is confusing the laws of exponents. When raising a power to a power, some students incorrectly add the exponents instead of multiplying them. The correct approach is to multiply the exponents. 1/2 times 1/3 equals 1/6, giving us x to the 1/6 power. A third common mistake involves negative fractional exponents. Students sometimes think the negative sign applies to the final answer, making it negative. Rather than understanding it, it means to take the reciprocal. The correct interpretation is that the negative exponent means we take the reciprocal. So 16 to the negative 3/4 equals 1 over 16 to the 3/4, which simplifies to 1/8. The fourth critical mistake is not verifying your calculations. Even when you know the rules, arithmetic errors can creep in. Let's look at a student's work on 27 to the 2/3 power. We can verify this answer by checking if 9 to the 3/2 power equals 27. Indeed it does, confirming our answer is correct. We can also solve it the alternative way by taking the cube root first, then squaring. To avoid these pitfalls, always write out each step clearly. Remember that fractional exponents mean root then power, handle negative exponents by taking reciprocals, and most importantly, verify your answers by working backwards when possible. Remember, mathematics rewards careful, methodical work. Taking time to double-check your steps will save you from these common errors and build your confidence with fractional exponents. Here's a crucial tip that will save you from making costly mistakes with fractional exponents. Always simplify the expression inside the parentheses first before applying the fractional exponent. Let's work through an example to see why this tip is so important. We need to evaluate the expression 2 to the 3rd power times 3 squared, all raised to the 1/3 power. Notice the expression inside the parentheses. This is what we must simplify first, before we can apply the fractional exponent. Step 1, simplify inside the parentheses. 2 to the third power equals 8, and 3 squared equals 9. 8 times 9 equals 72. Step 2, now we apply the fractional exponent. Our expression becomes 72 to the 1/3 power, which is the same as the cube root of 72. To find the cube root of 72, we can approximate this value. The cube root of 72 is approximately 4.16. Interestingly, if we had distributed the fractional exponent first, we would get the same answer in this case. However, this approach is more complicated and doesn't always work correctly. Here's why this tip is crucial. Consider 4 plus 5 to the 1/2 power. If we simplify inside first, we get 9 to the 1/2, which equals 3. But if we distribute the exponent, we get 2 plus the square root of 5, which is approximately 4.24. These are completely different answers. Remember this golden rule. Always simplify what's inside the parentheses first, then apply the fractional exponent. This order of operations will keep you on the right track and prevent costly mistakes. Here's our second essential tip for working with fractional exponents. When you encounter expressions with radicals, always convert them to fractional exponents before applying the laws of exponents. This simple conversion can transform a complex-looking problem into something much more manageable. Let's review the key conversions you need to remember. The square root of x becomes x to the 1/2 power. The cube root of x becomes x to the 1/3 power. The fourth root becomes x to the 1/4 power. And more complex expressions like the square root of x cubed become x to the 3/2 power. Let's see this tip in action with a concrete example. Suppose we want to multiply the square root of x times the cube root of x. In radical form, this looks complicated, but watch what happens when we convert to fractional exponents first. We convert the square root to x to the 1/2 and the cube root to x to the 1/3. Now we can easily apply the multiplication rule for exponents. When multiplying terms with the same base, we add the exponents. 1/2 plus 1/3 equals 3/6 plus 2/6, which gives us 5/6. So our final answer is x to the 5/6 power. This would have been much more difficult to see in radical form. Here's another example showing division of radicals. We have the fourth root of x cubed divided by the square root of x. Again, this looks complex in radical form, but becomes straightforward with fractional exponents. Converting to fractional exponents, we get x to the 3/4 power divided by x to the 1/2 power. Using the division rule for exponents, we subtract the exponents, 3/4 minus 1/2. To subtract these fractions, we need a common denominator. 1/2 equals 2/4, so we have 3/4 minus 2/4, which equals 1/4. The final answer is x to the 1/4 power, which we could write back as the fourth root of x if needed. This conversion technique works so well because fractional exponents allow us to use the systematic rules of exponents rather than trying to manipulate radicals directly. The arithmetic with fractions follows clear patterns. There's less chance of making errors, and it's much easier to see opportunities for simplification. Remember this tip whenever you encounter mixed radical expressions. Convert first, then calculate. Congratulations! You've successfully mastered the fundamentals of fractional exponents. From understanding how roots become powers to applying complex laws of exponents, you now have a powerful mathematical tool at your disposal. If this video helped you understand fractional exponents, please give it a thumbs up. Share your thoughts or questions in the comments below, and don't forget to subscribe for more mathematics tutorials that make complex concepts simple and accessible. Now that you've unlocked the power of fractional exponents, I challenge you to apply them to real-world problems. Use them to calculate compound interest rates, model population growth, or solve engineering challenges. The applications are limitless when you understand the underlying mathematics. What other mathematical concepts would you like to explore? Logarithms, trigonometry, calculus? Let us know in the comments below. Your suggestions help shape our future content and ensure we're covering the topics that matter most to you. Remember, Mathematics is not just about memorizing formulas, it's about understanding patterns, solving problems, and discovering the elegant logic that governs our world. Keep practicing, stay curious, and never stop learning. Until next time, keep exploring the beautiful world of mathematics.